through these. So our understanding of gas behavior comes from what's called empirical study, which is making observations. We watch how gases behave, and then we make some predictions about what's going to happen under certain conditions. So we have a few thought experiments for you. Number one, if you consider a beach ball, some observations we can make are what happens to the beach ball when I leave it outside all year long. The temperature changes, so the volume changes. In the cold weather, when the temperature drops, the volume drops. And when the temperature goes up, the volume increases. A soda can, what happens when I leave a can in your car? Well, if the temperature goes up, the pressure goes up. If you open the can when it's real hot, you're going to have a mess on your hands. So temperature and pressure, we've observed, behave directly. This is what's called a direct relationship. They both either increase or decrease at the same time. Pressure and volume don't always behave that way. What happens when I pump up a bike tire? Well, you're putting more air in, so the amount of gas goes up, the volume goes up, and the pressure goes up. So those are observations that we've made, and they help us understand and come up with these different gas laws. So the four variables I'm talking about are temperature, volume, pressure, and moles. You can pretty much use any unit you want to express these except for temperature. For temperature, when you're using these equations, you have to express temperature in Kelvin. You can't use Fahrenheit or degrees Celsius. It won't work. The relationships described above are always true for a gas. These are laws of the behavior of gases called the gas laws. And I'm going to show you where they come from and how we derive them. These were developed by observations that describe the behavior of gases in empirical terms, that is, properties that a person can directly observe and experience. Gas laws explain how a gas behaves, but why do they behave that way? The answer lies in the fact that we picture gas molecules and atoms as moving according to this theory called the kinetic molecular theory, KMT for short. But the observable properties of a gas are the consequence of the actions of the molecular motion of the gas sample. So we need to look at the atomic and molecular level to fully understand what's going on inside a gas sample. So let's just go through these, what are called postulates, which are another word for assumptions about gas behavior. Number one, a gas consists of particles with a negligible mass and negligible volume. Actually, with these formulas you can calculate the mass, so I'm not sure why it says that there, but we assume they have negligible volume. What that means is we assume that the container that holds the gas is the only volume you have to worry about. In reality, you should have to worry about the volume of the gas particles, but that volume of the gas itself is so small that we can ignore it, and we won't get an answer that is too far from what would be considered the correct answer. So when we assume the volume of the gas particles themselves, whether they're atoms like in helium or molecules like in carbon dioxide, the volume of those particles is assumed to be 0. So the volume available to the gas is equal to the volume of the container. The second assumption we make about gas behaviors is they travel in random straight line motion, kind of like on a pool table when the billiard balls are bouncing all around in every direction. That's the way we picture gas molecules in a real sample, but in 3 dimensions. However, they move at very high velocity. Believe it or not, gas particles move around 400 meters per second, even at room temperature. So it's very high speed. We don't feel that because the particles themselves are so incredibly small. They're on the order of about 10 to the negative 22nd grams. All right, number 3, when gas molecules collide, no kinetic energy is gained or lost during the collisions. In physics, we call that an elastic collision. Energy can be transferred from one molecule to another. So it's like billiard balls hitting on a pool table. The energy of one gas molecule hitting another one is completely transferred. There's no loss of energy. In reality, there is a little bit, but we're going to ignore it. Number 4, gas particles don't interact with each other or the walls of the container. There are no forces of attraction. Attractive forces are very weak. We'll assume there's 0. That makes the math a lot easier. Number 5, a collection of gas molecules will have an average kinetic energy that is proportional to temperature, and it's 3/2 RT. So it's the higher the energy, the higher the temperature, the higher the energy. As temperature goes up, things just move faster. They bounce around the container faster. They hit the walls of the container with more force. But you can see this is kind of how we picture a gas, just a chaotic system of atoms and molecules bouncing around in 3 dimensions, hitting the walls of the container. That's what creates pressure, bouncing off each other, but there's no loss of energy when they bounce off each other. So the overall kinetic energy, or what we call the average kinetic energy of the system, is dependent on temperature. The reason why we say it's average kinetic energy is because some particles are going to be moving faster or slower than others. They don't all move and bounce around with the same velocity. The temperature in this equation is what's called the absolute temperature, which is the Kelvin scale. The reason why we had to do that is because if we plug in negative temperatures like you see here, absolute 0, which is 0 Kelvin, is equal to negative 273 degrees Celsius. You can't plug in a negative number into some of these equations because that would give you a negative result for things like pressure and volume, which it makes no sense to have a negative pressure or a negative volume. So please keep that in mind when you're doing practice problems, that you must have temperature in Kelvin. And the relationship between Celsius and Kelvin is simply to add 273 to the Celsius temperature to get Kelvin temperature. So the nice thing about kelvins and degrees Celsius is that the degrees themselves have the same size. They're just, the 0 point is different. Now the limitations of this model that, like I said, we assume are 0, is the gases actually do have a volume. Think of the definition of matter. Matter is anything that has mass and takes up space, so that has volume as well. Gases can and do interact with each other in the walls of the container. There can be attractive forces and repulsive forces. Again, we're going to ignore those, so the formulas are not too complicated. What we call this situation for a gas is an ideal gas. It obeys these 5 assumptions or postulates. All real gases, all gases which are found in nature, will deviate from this behavior depending on how big they are and their ability to interact with other molecules. This is most often when the particles are close together. So under what conditions would pressure and temperature, what conditions of pressure and temperature will the molecules not behave ideally? Well, that would be at low temperature and high pressure. So the situations we're going to discuss in applying these laws is pretty much around room temperature and atmospheric pressure on the surface of the Earth, which works for us because most situations we would find ourselves in dealing with gases would be at a pretty moderate temperature, around 25 degrees C and around 1 atmosphere. At those conditions, gases do behave ideally, and they follow these equations which I'm about to talk to you about. So the 4 variables that I mentioned earlier that describe the behavior of a gas are these. Pressure, so some new symbols for you to learn are capital P for pressure, capital T for temperature, capital V for volume, and small case, lowercase n for moles. The units we use for pressure, some of the common ones are what's called atmospheres, millimeters of mercury, a torr, which is named after an Italian scientist who I believe he invented the barometer. His name was Torricelli, so they named one of the units of pressure in his honor as a torr. The nice thing is a torr and a millimeter of mercury are the same size. 1 atmosphere pressure, which is the unit we're going to use because it's comes out to be about a nice number of around 1 for sea level atmospheric pressure. We could just call it 1. So that's a nice unit to use. And sometimes, especially if you're pumping up your tires at the gas station, your gauge that you use will read what's called pounds per square inch, which is shorthand PSI. I'll show you a few sample problems dealing with that unit. But you can use any unit you want in these problems. The most common are atmospheres of pressure and millimeters of mercury. The weatherman will often express the conditions of atmospheric pressure in inches of mercury, which just comes from the fact that when they invented the barometer, they used a column of mercury to measure the atmospheric pressure, and that's where this Hg comes from. That's the element symbol for mercury. A barometer just uses the element mercury to measure pressure, as I said. But you can look that up on the internet if you're curious what a barometer looks like. I don't think there might be a picture in the textbook. For temperature, again, we have our 3 common scales. You're going to be given a lot of sample problems that might give you degrees C. You must convert it to Kelvin. We won't deal with degrees Fahrenheit too often in these problems because it's not the SI unit. This is the SI unit. We want to use Kelvin. And notice there's no degree symbol on the Kelvin. It's just a capital K. So it's a little confusing. It looks like an equilibrium constant, but it's actually the unit for temperature. And again, the relationship between Kelvin and Celsius is just to add 273, to be exact, 273.15 to get the degrees Celsius converted to Kelvin. When you use volume in these equations, it's most common to express volume of a gas in liters or milliliters. Just remember 1,000 milliliters are in a liter, or 1 milliliter is 0.001 liters. The amount of gas, we will use the symbol N, that's moles of gas. So recall from our discussion of stoichiometry, converting from grams to moles is pretty simple. Just take the mass in grams and divide it by the molar mass in grams per mole, which is shown here in multiplication form. So again, the typical problem is to give you 3 of those 4 and ask you to solve for the 4th. Let's just talk about a few of these variables in a little bit more detail, especially pressure, since it's something we don't talk a lot about. But this is kind of like a basic physics discussion as well. What is pressure? What causes pressure? Well, the most elemental definition of pressure is it's a force per area. So you can imagine in a gas sample, the particles are hitting the walls of the container, and this is just you got to imagine this is sort of the inside wall of a vessel, and I've just drawn in red here a part of the wall, a piece of the wall that the gas particle hits. Let's picture the gas as just a black sphere. It hits the wall with a certain force, represented by capital F. So the amount of force it hits that area of the wall divided by the area is what's called pressure. And the gas moves with a kinetic energy proportional to its velocity. So the higher the temperature, the faster the gas particle moves, the more energy it carries, therefore the more force it imparts. The higher the force per unit area means the pressure goes up. So that's really all pressure is. Higher pressure is just particles are hitting the walls of the container with more force because the temperature has gone up. Now if you look at the formula, pressure is force per area. The SI unit for force is called a Newton, after Isaac Newton, the English scientist. So we call it capital N. Area, the SI unit of area is square meters, so meters times meters is square meters. Newton per meter squared. They decided that that was too much to say, so they changed that, or they just call that a Pascal. There was another scientist, I think with that name, they named it in his honor. Capital P sub A is the unit for a Pascal. That's the SI definition. But in the problems that we want to do, the Pascal isn't really the most convenient unit. It's a very small unit. Notice 1 atmosphere pressure, which is pretty much the atmospheric pressure that you and I experience every day, sea level, or even at this level where we live. We're not exactly at sea level, but close enough. The atmospheric pressure we experience every day doesn't vary too much from atmospheric pressure. But at 1 atmosphere is 101,325 pascals. So this is a tiny, tiny number. So we're going to find it more convenient to use the 1 atmosphere, or the atmosphere, as our unit of pressure. Let's just think about pressure in terms of numbers of molecules. How do the number of molecules, how is it related to the pressure? Well, pressure is directly proportional to the number of molecules. You'll see this unit a lot, or this symbol a lot in these videos. This looks like a fish. That means proportional to. When I say something is proportional to something else, what I mean is it can be either directly proportional or inversely proportional. Directly proportional just means as one variable goes up, the other one goes up. As one decreases, the other decreases. You're always looking at the relationship of one variable to another. You can really only focus on 2 variables. How does one affect the other? What I might say something is inversely proportional, like in Boyle's law, you'll see in a few minutes here. Boyle's law says that the pressure of a gas is inversely proportional to volume. So as one goes up, the other one decreases, and vice versa. So if you have, for instance, let's say we have a container filled with 12 molecules of nitrogen. Let's say we measure the pressure to be 640 millimeters of mercury. If you cut the number of molecules in half and only have 6, since pressure and number of molecules is directly proportional, you would cut the pressure in half. Or if you have a mixture of gases where you have 6 molecules of oxygen and 6 molecules of nitrogen, the pressure would be exactly the same as it would if there were 12 molecules of nitrogen. So that's the nice thing about this kinetic molecular theory. The identity of the gas has nothing to do with it in determining things like pressure. It's just how many particles are in the container that will matter in determining the pressure. And the total pressure there's a famous law called Dalton's law of partial pressure. It's pretty simple to understand. It just means if you have a mixture of gases, in this case we just have 2, the total pressure inside the container is simply the sum of the partial pressures of the individual gas particles. So in this case, if we have 6 nitrogen molecules and 6 oxygen molecules, and they have a total pressure of 640, what Dalton discovered was something pretty simple. If there's half the vessel is filled with oxygen and half the vessel is filled with nitrogen, therefore half the total pressure is the pressure of nitrogen, 320 millimeters of mercury, and half the pressure inside is due to oxygen, 320 millimeters of mercury. But they add up to give you 640 millimeters. So when we combine a lot of these laws, we come up with this very famous equation called the ideal gas law. I'll just call it IGL. PV equals nRT. So please always use capital P, capital V, lowercase n, capital R, and T. R is a constant called the ideal gas constant. Whenever you have an equation, you have to always throw in a constant that makes it, turns it from a proportion symbol into an equal sign. It's called a constant of proportionality. That's a lot to say. But in this case, it's R, and again, you'll see this a lot. You'll be using this number a lot. It's known to maybe 10, 20 digits, but we're just going to use it to 4 decimal places. 0.0821 liter atmospheres per mole K. Notice the units on R are very important. Capital L means the volume must be expressed in liters, pressure must be expressed in atmospheres, amount, N is in moles, MOL, and temperature is expressed in Kelvin. Notice also that the units of R have the units of all of the four variables. So these are called variables. PV, N, and T are variables. What that means is that they can vary, they can change. We can control their values. But the R is a constant, it never changes. This law relates the four variables. It's based on the assumptions of the kinetic molecular theory, and it works very well at predictions around room temperature and pressure. So what I want to do now is talk about where this law came from. It just didn't appear out of nowhere. There were 3 or 4 major experiments done that helped other scientists derive this law. The first important experiment was done by Robert Boyle, who lived from 1627 to 1691. He was one of the first scientists to come up with one of these special cases of the ideal gas law. Back then they didn't call it the ideal gas law. He was just looking at the relationship between pressure and volume. So what he noticed was if he had so you'll notice in all these cases I'm going through, you have certain conditions that must be met. For Boyle's law to hold true, for this to be a true statement, you have to have a closed container, which means constant volume of gas. So N is a constant, and temperature is a constant. Notice then, if these are constants, which means they just are a set number, nRT doesn't change. It's just some number, and it never changes. We can say that if PV is equal to a constant, then any situation, any value of P times V under any condition will be a constant. So you'll see this in all these examples I'm going through. We'll have 2 conditions. Generally, that's how we do these problems. We take a gas under a certain set of conditions, we'll call condition 1. That's usually considered the initial condition. And we'll change one of the variables, it doesn't matter which one, and we'll have a new set of conditions, which we'll call subscript 2. That would be considered the final condition, initial, final condition. So it comes from the fact that if this is a constant and this is true, PV equals nRT, then any PV product is going to be true. P1V1 equals P2V2. And I'm going to go through each one and give you some practical examples for each law. So Boyle's law talks about this in your textbook as well. Simple breathing is an example, or it's an illustration of Boyle's law. Volume goes up, pressure goes down. So what happens when you breathe, when you inhale, your lung cavity expands, the volume goes up, therefore the pressure inside your lungs drops. If the pressure inside your lungs drops, it means atmospheric pressure, which we'll call P outside, is greater than the pressure inside your lungs. So gases always move from high pressure to low pressure. That's kind of like how weather patterns work. Weather systems move from high pressure to low pressure. Same thing here. Gases move from high pressure to low pressure. So in this case, when you breathe in, the atmospheric pressure outside, the air rushes into your lungs because of this discrepancy in pressure. Exhaling causes the opposite. Exhaling means that your lung cavity shrinks, the lungs shrink, therefore their volume drops, and the pressure inside of your lungs is now greater than the pressure outside. If the pressure inside is greater than the pressure outside, air will then rush out, and it just goes back and forth, on and on. That's an illustration of Boyle's law. Notice it's done at constant temperature, body temperature, and the amount of gas inside is essentially a constant. It's just the volume of your lungs is a constant. But we call that, it's key here to understand that we call pressure and volume inversely proportional, which means as one rises, the other falls. As the other one falls, the other one rises. We can represent that graphically with a picture like this. You can graph pressure and volume on an y and x axis. It doesn't matter if you put P or V on the x or y axis. They both give you the same sort of graph. It looks like a curve. I guess it's an exponential or logarithmic curve. In this case, it would be, you would read that as pressure is inversely proportional to volume, or in this case, you'd say volume is inversely proportional to pressure. In any case, this is Boyle's law written instead of subscript 1 and 2, it's initial conditions and final conditions. So we'll do a few examples. Sorry, that might be out of camera view. We'll do a few examples of that, that law. I'll try to do an example of each of these after I've gone through them to show you where the ideal gas law comes from. All right, we're at 28 minutes, so I'm going to probably stop this video, and we'll continue with the next law, which is called Charles' law, in the next video.